Hello.
Yes. Thank you. We talk. John's going to talk about what you always wanted to know about mathematics, but were afraid to ask. So I'll hand the phone to you, John. Okay.
Can you all hear me? I have a body mic. My body mic should make you able to hear me. Can you hear me okay back there? Can you guys hear me? Can't turn the. Can you hear me back here? Now, that was not me. How about now? You can hear me well? Can you see? Can you see? Okay. Um, I'm so happy to be able to share this with you tonight. Tom Richardson was going to be my host tonight, but he's ill, so Rajiv has taken over. I really appreciate your hosting this for us. Great warm up. Um, this was the title that I gave because Tom asked that sometime a long time ago I give a title for a talk. I had no idea what I was going to talk about, so I just gave this as the title. And later on, Jim Coppinger asked me what I was what does that mean? So I wrote something else out, uh, and and then when I started thinking about what I was going to tell you, I looked at what I had promised I would tell you, and got really frightened. But it's an intriguing idea, and I'm eager to share that with you. So that's the kind of the disclaimer. I'm not claiming to know a lot, but I'm just claiming to be interested in this question. So to get us started, I thought I would play a game, and it was going to be Tom who was my partner, but now it's Rajiv. He's agreed to play this 15s game. Um, the way you play it is this: I have a I have I have 9 cards here, 1 through 9. I'm going to lay these out on Rajiv's table. This is where Rajiv is going to be playing, and these are the cards 1 through 9. I'll give them out here. 1, 2, 3, 9, 6, 8, 7, 5, 4. Okay, 9 cards.
Sure.
Okay, ace is low, and the way we play is that we take turns playing. And we each of us draws a card. You draw a card, and then we draw a card. Then and then Rajiv draws a card, and the first who can make no, you can choose. You choose. And we'll both choose, and when we choose our card, we'll ask you to remove it from play. And what you mustn't do is look at my screen. You don't look at the screen. Okay. So here.
Okay.
Okay. So let's get started here. So this is the set of numbers that we will use. You mustn't look at my at this either.
I'm looking here.
There you go. Pick a card. Well, tell us what it is. It's a 5. Okay. We will circle our 5 to remove that from play. Now, what would you like to? What shall we choose? Do you think? Somebody says 8. Okay. We will cross out 8 to remove that from play. Okay. Your turn, Rajiv. We're playing 8 now. It's your turn, Rajiv. The first person to get 3 to make 15 wins. Three cards, not four, not two, not an eight and a seven. That's only two cards, and not one, two, three, nine. That doesn't work either. That's four cards. Your turn. Yep, six. Oh, we're gonna cross that out. What do you guys want? What we need three cards only. You have to have three cards. Yep. I think I said that. I think I did. Yes. So you guys want me to cross out the four? Okay. There you go. And your turn, Rajiv. He wants to win. He's going to take the three. Good move, right? Good move. What are we going to take? We're going to take the seven. We have to take the seven. Otherwise, he takes the seven. Now you're going with the ace. Okay. That's a good move. What are we going to take? Nine. Yeah, that's right. That's right. That's right. Yeah. Okay. I was so excited about playing this game, but nobody won, right? Nobody won. You can turn around and look at what we're doing now. What we are doing is playing tic tac toe, and what you were doing was playing the 15s game. The 15s game is scary because you don't know how to which card to use next. It's kind of a welter of confusing experience. We had the advantage over you by organizing our approach to this game and in a tic tac toe fashion. I got this idea from Martin Gardner. This is my Martin Gardner idea. Thank you, Rajiv. Give Rajiv a hand. But there's a lesson in this, and the lesson is that um, there are two equivalent things. There's the 15s game that Rajiv was playing, and there's the tic tac toe game that we were playing. And these two things are isomorphic, and they're the same kinds of the structure is the same. There's a structure preserving association between the 15s game and the tic tac toe game, and I think of this as a metaphor then for the way language works. And I've given you the the, um, the etymology of metaphor. For means carry or bear. Meta means over, beyond, or across. So what I'd like to think about now is how language works as a metaphor. Do you grasp that? Do you understand that? Those are both metaphors in the way we're using this idea. And I'm thinking about where metaphors come from and how they work in language. So I've just been thinking about the sources of metaphor in ordinary language that you and I are using right now together. We um, are talking about actual occasions, the occasion of us eating together or of whatever we're doing in ordinary language, and the constraints on that collection of metaphors and that collection of words is really just related to ordinary experience. But I'm thinking now about mathematical language and what its constraints might be. Where does mathematical language come from and what is it about? It's not necessarily about actual occasions. This, the mathematical objects are not of this world. There is no circle except as how we think of it. There is no straight line except as how we think of it. Pi is a subject of our imagination. It resides there. It does not reside anywhere else. And so the mathematical language that we need to that we develop is going to be one that whose metaphors come from our imagination itself. And I'm thinking now about the constraints on language that we have in ordinary language, which comes from ordinary experience as we know it, versus what the constraints might be on mathematical language that comes from our imagination. What are the constraints on our imagination? And I'm thinking that there are two. There, 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 there's grammar and there's logic. That's it. If I can say it and if I can conclude something from what I said, those are the only constraints that I've got in mathematical language. So I've got this imagination that is in my head, and and Andy's got imagination in his head, and I wanted to tell Andy what's in my head. I've got to use language to get across there, and as mathematical language will awaken up mathematical responses in Andy. So that's the kind of the places where the place where we begin tonight with watching mathematical language as a structured association with actual experience. I had this diagram that I use to sort this out, and I've called it the welter of ordinary occasions down here. This is the world that your cat lives in. This is a world of unevaluated experiences and occasions that just happen, and we might be part of it or not. And then up here, I have structured mental activity, which is an attempt to make some kind of sense out of this welter of ordinary experience. How does it work? I start with a question about the world I live in. And I express that question using mathematical language, or if it's philosophy that I'm doing, I have a question about what the meaning of life is. Whatever, I put this unevaluated experience into some kind of structured mental activity, either ordinary language or mathematical language. I ask that question in that context. And then I have lots of ways of analyzing that question that I've made by language, and I get some kind of an answer to that mathematical question or this linguistic question. But the conclusions uh, are going to be useful only if we interpret back into an answer to the actual question that we began asking about. So this is what I think is going on whenever we are using language to think about the world that we live in. Either ordinary language, the books we read, the philosophy we study, or mathematical language. But there's always this translation from the larger world that surrounds and supports us in all that we do, but that we might not have complete understanding of, and pieces of that larger world that we can represent by structured human activity. That's the picture that's going on when I'm thinking about doing mathematics and applying mathematics to the real world. So the how we doing? So can you see okay? Can you hear okay? Are you with me so far? Okay. Thank you. Thank you. Okay. So this is a big title for everything you want to know about mathematics, but we're afraid to ask. But it turns out that this is the flavor of this talk tonight. We're going to look at a specific example of how language has evolved to accommodate imagination and how imagination has followed that language in the evolution. So it's going to be a quick tour of cosmology, and I'm only going to be able to touch the very highest points and just most superficial way. But I think that I got to tell the story. So here's the story begins for me and tonight with this with this with the um, the the cosmology of the Greek mathematician Ptolemy, who lived from 100 to 170 in the Christian area. The only book that we have of his was written at about 150 after in the Christian era, and it posits a geocentric model for the planetary rotation with the sun at the center. There's some problems with planets. They're wandering, and so you can't just say the planets are hanging on these crystal spheres, as Ptolemy said the stars were hanging on, but instead there are epicycles that are attached to the crystal spheres, and then things don't work quite out, so he has to use deference, and he introduces all kinds of new modifications that model to make it fit his observations until finally the model itself it collapses under the weight of its own modifications. The Ptolemaic universe is pretty good. The Ptolemaic model is pretty good for describing what we see as shepherds in the fields. It's not very good for more refined observations that we might make later with the aid of telescopes and other things. So we finally have to abandon this model, and the best um, uh, model to follow is the model of Johannes Kepler. Here's Johannes Kepler in the late 16th century, and I want you I I want you to just think back on the picture of the circle and the Earth at the center. Those metaphors are close to hand. It's way easier to draw a circle than it is to draw an ellipse. But but Kepler, if you can see the diagram here, Kepler is positing and that the sun is no longer the center of the circle that the planet is traveling on, but it's a focus of an ellipse, and the planetary motion is actually elliptical around the sun as one of the focuses. These are the three laws of that Kepler. Is amazing that he takes this data and he can see that the elliptical the orbit is an ellipse with the sun as a focus. He can see that, and this is the great thing about Kepler, that this if you take a line from the sun to the planet and the sun to the planet, that line sweeps out a kind of a triangular looking thing. And what he observed is that equal time sweeps out equal area. Those two areas are the same. He writes that down. He gets data for that. He also observes that the square of the orbital period is the cube of the semi-major axis. The semi-major axis is the long half of the long axis. Those three laws are Kepler's laws, and as you look at them, you don't see the word velocity in these laws. The speed is not there. I think you can see average velocity. When we think about velocity, we think about miles per hour. And if I take an hour to go 60 miles, then I divide that 60 by one, I get 60 miles per hour. And or if I want to calculate the velocity of something, I always calculate how far I've traveled divided by how long it took me to go. But that little calculation that I just described that we all do, that is actually average velocity. Because sometimes, let's just think about that. Okay, it took me an hour to go 60 miles, but sometimes my speedometer was showing 80, and sometimes it was showing 40. The difference between average velocity and instantaneous velocity is key, and it will come up later. But there's nothing about instantaneous velocity in Kepler's laws, But um, because he didn't have a way to do that. But the next the next guy I'm going to talk about is Isaac Newton, whose laws of motion posit that a particle moves in a straight line at a constant speed. There's speed right there, speed. And he has in mind instantaneous speed, not average speed. And the second law, force equals mass times acceleration. Acceleration is change in speed, the rate of change of speed, the rate at which speed is changing with respect to time. Also, an instantaneous rate of change. And the third law is the equal magnitude in opposite directions. But um, the other the other law that Newton gave us when he was thinking about planetary motion was the law of universal gravitation, which again involves acceleration through force, but it's that the force is proportional to the product of the masses and and inversely proportional to the square of the distance between these two masses. So there's this inverse square law that he uses, and together with the his three laws of motion and the law of universal gravitation, he is able to derive all that Kepler observed. So now he has a language to talk about motion and to talk about gravity, and from this language that he's developed through his principi his thinking, he is able to derive what Kepler had had actually observed through observation. And he does this by means of infinitesimal calculus, which is really a way of doing instantaneous rates of change. Maybe I'll write this over here. If I divide distance traveled by time elapsed, that's a fraction. And if both of those numbers are non-zero, then or if t is non-zero, then I'm okay. But but when these are both infinitesimals, there's no arithmetic that allows us to compute the ratio of two infinitesimal things, um, two things that happen over an instant. And it's Newton's great gift to the world of mathematics and probably the world of science that he gave us through calculus a way of calculating infinitesimals, either the quotients of infinitesimals, as in the instantaneous rate of change, or sums of infinitesimals, as in length and area questions. So that's his big contribution. And now I'd just like to walk through a few um, uh, uh, developments that um, came from that ability now, this sudden ability to calculate infinitesimal rates of change. The first contribution comes from Leonhard Euler in 1736. He's able to talk about geodesic curves. Instead of something being this, we think of the straight line as being the shortest distance between 2 points, but that's if the straight line is on a plane. But if the space that we're living in is curved, then the shortest distance from one point to the other on that surface is not going to be a straight line. It's going to have to be some line along that surface. And it was Leonhard Euler who first figured out a way to use calculus to talk about geodesics. We live on a sphere, and the shortest distance from one point to another on our sphere is one that actually is along a great circle that if extended would just be an equator of it would cut the sphere in half. So Euler allowed us to talk now about geodesics, and instead of talking about an object unaffected by acceleration moves in a straight line, he can say that the object moves along a geodesic. Next big contribution to this evolution of language of cosmology is Gauss, and he was able to talk about use the same language to talk about curvature. I've given you a simple example here of a paraboloid, and I've given you some cartoons here. This red arrow is intended to point straight out, a normal vector to the surface. And this vector is intended to point straight out. Do they look like they point straight out from that surface? Not to Ross. I'm sorry, Ross. But how about this? How about this? This is the vector, my head. Is this pointing straight out? Okay, okay. Now, what does curvature have to do with rate of change? This is my tiny little head here. And keep track of where that normal vector is pointing. It's changing, isn't it? What is its connection? How fast is it changing with respect to how I move along this geodesic on my head? There's a rate of change there, isn't there? The rate at which the vector changes divided by with respect to the distance I've traveled along, in this case, my head. But can you see that really curvy things have this thing? I mean, a really flat head would not. It wouldn't. That arrow would not change as much as on a little tiny head like mine. You can see it. That's the definition of curvature that Gauss actually makes precise, and he's now able to talk about the curvature of surfaces. You still okay? Am I okay? I'm not sure. This is so hard to talk about, and I'm shoving volumes under the rug here. But the next big step in this evolution of the language we're talking about is the Bernard Riemann. Two things about Riemann. First of all, check the dates. 1826 to 1866. 40 years old. He was dead by the time, I mean, 40 years. Mozart died when Mozart was 35. Schubert died when Schubert was 33. This is the the early snuffing out of profound genius is just one of the tragedies that we have. Um, in those days, to become a full professor, you had to write a what's called a Habilitationsschrift. And Riemann chose to write on the hypothesis that lie at the foundations of geometry. And in this Schrift, that was his application to become full professor, he is able to talk about all this differential geometry that Gauss and Euler have developed, and he's able to put that into a much larger, higher dimensional setting. And he's able to talk about even something he mentions in this paper as space-time. And he does this in 1854. All of these ideas are developing independent of the applications that that are made of them. I'm not saying that this is happening in a vacuum. There's constant communication between the questions about thermodynamics and electromagnetism and these mathematical ideas. But there is a world of mathematical imagination that has expression, and these guys are talking to each other in that world. And pieces of that world come to be this kind of structured human activity that is able to answer questions about that world. And 60 years after Riemann's habilitation shift, Einstein finds that language from that paper of 1854 to be exactly the language he needed to express his ideas of special relativity. So this is almost the end of this chapter of the evolution of that cosmology language, but it's beautiful to think about that there's a world of mathematics that runs parallel to the world that we live in, that our cat woke up in this morning. That world of mathematics that we have access to through our imagination and language. That's a kind of a companion to this other world that we are born into. I think of mathematics as the other invisible power, God being the other one. Both of this world evolves almost in step with us, or we evolve in step with it. We evolve in step with it. So I've been thinking about how language itself evolves, and I've been looking at the just thinking about the evolution of philosophical ideas that are pretty much focused on ordinary human experience, and the evolution of mathematical ideas that are focused on the imagination that accompanies that experience. And I'm thinking about what is it that allows allows these concrete languages of ordinary experience to thrive, to grow, to evolve. Well, it must be truth. It must be that these statements that we find ourselves making in ordinary language end up being true about the situation that we find ourselves in. Truth is the companion. And by truth, I mean a positive association between ordinary experience and the thing we're expressing. Well, I didn't know that imagination lived over here, but here it is. Um, the uh, mm, I just lost my point of view. What was I going to say? The real world. Um, uh, I know, I know, I know, I know, I know. If if truth is the companion to the development of ordinary language, is the companion to the development of mathematical language, because these things don't yet have models. They don't have a home in the world that we live in yet. It took a long time for Riemann's ideas to get into Einstein's language. What accompanies that development? And here's what I think. I think it's beauty. I think beauty is the thing that allows mathematical ideas to grow and thrive. And truth is the vehicle that allows ordinary language to grow and thrive. That's what I've come to. And I'm not alone in this. Um, French mathematician Henri Poincaré, 1854 to 1912, he he observed that when he would think hard about something, nothing would happen. And then he would go to the beach and relax. And then he talks about the incident of coming back from the beach to the bus and putting his foot on the step of the bus. And suddenly the thing he'd worked so hard to solve, the solution just came to him. And he ran home and he didn't even have to think, it just was all there. And he wonders, what is it about all this mental activity that allowed this to happen? And he likens mental activity to kind of a stew, and you're just swirling it around. You don't know really what's happening. You don't know what's coming up or anything. You just swirl it around, and then you go away, and it keeps swirling around. And some things, some things that have swirled around rise to the top. And those are the ones that catch your attention. And you wonder, what is it about these things that catch my attention? Well, he writes, what is the cause that among the thousands of products of our unconscious activity, some are called to pass the threshold, while others remain below? What is it about those ideas? Well, the useful combinations are precisely the most beautiful. That's what he wrote in 1908, about the same time that Einstein was writing his paper on special relativity. But I think that beauty is one of the key criteria for this development of mathematics. And I think that with that, I'm done with the serious part of my talk. You might not get it right. Oh, right. I love that. Okay. Okay. So that was the cue. That was the cue. Ross got it. Well, Ross got that. Right. So Mike and I were talking about this talk a couple of months ago, and I said, this is serious. Well, let's make it a little bit light. So I have one diversion that I prepared for you. Do you want to hear? What do you want the diversion? Okay. That you have to say yes to this. Okay. Okay. Then we'll have some time. If you have questions, I'll be happy to answer questions too. But let me think about the diversion. I for this I need a somebody to supply me a secret number that I don't know. Uh, You're Gary. Can you write down a secret number up on here and bring it. I don't want to see it. I don't want to see it. I don't want to see it. Gary's going to give us a secret number between between one and Gary. Are you okay to get up and put it on the overhead? Okay, Gary's gonna write down that number and he's gonna show it to you all, and you all are gonna make note of it, and then um, we'll move into the next little diversion. So a number between 1 and 63, a number between 1 and 63. Has he done it? Is it a number? Is it between 1 and 63? Okay, take it away, Gary. Is it gone now? I don't want to know what it is, but I will know what it is because you're going to be thinking about what it is. Are you thinking about what it is? Okay, thinking hard about what it is. Okay, that's all I need. That's all I need. Okay, as you're thinking about that number, I'm going to show you some possibilities. And what you need to do, you can sit down now. Thank you. Give Gary a hand. There are some possibilities. Is it one of these numbers? No. Yes, we have to resolve that dispute. Is Gary's number on that card anywhere? Joe says no. Well, it's not there. It's not there. Okay. Okay. That is not there. Okay. Well, um, how about this one? Is it there? It's there. Oh, it is there. Okay. Good. How about this one here? How about this card? Is it there? No. Okay. No. How about this one here? Is it there? No. Okay. How about this one here? Yes. Good. Okay. Wow. And how about this one here? 13? 13? Oh, it's 13! Want to do it again? You have to know your numbers. And let's just go through this slowly here. 1, 2, 3, 4, 5, 6. I got 6 cars. And you said it was on that card, right? And there's 13. It's right there. And what did you say about this one right here? Yes, it's on that one right there too. And what did you say about this one right here? Yeah, yeah. Okay, those are the cars that it was on, that it was on. And do you notice anything about the upper left-hand corner of that card? 1, 4, 2, 8, 13. let's look at the cards that 13 was not on, and look at the upper left hand corner. There's a 32 there, and there's a 16 there, and there's a 2 there. What do you notice about 16, 2, and 32? Powers of 2, 1, 2, 4, 8, 16, 32. Elizabeth Cross, give us a number. It's okay. Fine. It's fine now. Go ahead. Between no, but like what Gary did. One between 1 and 63. 48. She's got 48. That's a number between 1 and 63. Let's play the game again. Okay, here we go. Here we go. Here we go. Here we go. It's 48 on this card right here. I don't see it. Okay. I'm going to put it over here. It's 48 on this card here. No, put it over there too. It's 48 on this card. Yes. Okay, I'll leave it here. Is 48 on this card here? Yes. Oh, I'll leave it there. Okay, it's 48 on this card here. No. Okay. And what about this card right here? No. But I mean, you sort of figured that if when you look at the upper left-hand corner here, 60 and 32 are you got yeses for those. So what we're doing, you guys got I got party favors on your everybody got party. Look at nobody has opened this up yet. The party favors are all here. There they are, right there. I don't know. I figured you'd already see it. Everybody got party favors on their table. Yeah, there you go. There we go. Um, these are uh, I cut them into strips, but I just didn't have the heart to actually cut them into six little cards. You can do that at home. This is for your grandchildren here. This is a trick to impress your grandchildren. If you look at the upper left-hand corner of each card, it's a power of 2. 1, 2, 4, 8, 16, 32. And it turns out that any number can be expressed as a sum of powers of 2, just like any number can be expressed as a sum of powers of 10. 48 is four ones plus plus 8 10. No, it's 8 ones plus 4 tens. Um, uh, but the, the, the binary representation of 48 in this case was a 16 and um, 32. So any number has a um, a, uh, a binary representation, and what you were giving me when you were saying yes and no, when you finally figured out what the number was, um, was what the binary representation of that number was. So I'll give you another example here, and this will be just about the end of our time together. I'm calling this a binary diversion, and what I would like for somebody, Barbara, could you give me a number between 130 and and 200 there? 121. Okay, Barbara is giving us 142. Okay, so that's Barbara's number is 142. And John Geisler, what about you for a number now between 180 and 255? 213. Okay. Okay. Now I have a little um, program on my telephone here that will. That, no, not cheating at all. What rules am I cheating? I'm going to enter a decimal number, and the decimal number that I'm going to enter is 142. 142. And I'm going to convert it to binary, and it says the binary number is 1010001110. 1110. That's what the A is. And the B is, I'm going to reset that to 213. John, your number was 213. Oops, 213. 213. My thumbs are so fat. 213. 11010101. 11010101. And what that means is that the number 142 is 2 plus 4 plus 8 plus 32. 2 plus 4, 8. Oh, no, 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 John. What? Two, two, but two, yeah, 2 plus 4 plus 8 and plus 120 plus 128. I'm almost at the end of my capacities here. Anyway, I want to take these numbers now, and I've been looking forward to this for a while. I want to turn these into a binary canon. So here's what we're going to do. We're going to take the number A, which was 10001110, 1110. That's that number. And B, that John said who was very rich. 1101, 1101, 0101, 0101. Okay. Okay, there we go. Are you ready? What we're going to do is clap this out. Or if your clap doesn't work, make a bang. Okay? But we're going to make a noise. We're going to make a noise with each one, and we're going to be silent on each zero. Let's try A. I'll bang here. Let's try A. Are you ready? 1, 2, ready, play. Ah, 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 ah. How was that? That was good, right? Okay, let's try the next one. B. Let's try B. Ready, go. 1. Ah, ah, ah. Okay, you're great. Let's do A, then B together. So we all play the same song. Are you ready? Yes, you're ready. Okay, here we go. Okay, 1, 2, ready, go. 1. Ah, 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 ah. Okay. Now, this side starts first. You do the A, and then you go to B, and then you repeat. This side is quiet while they start, and then we start the A and do the B. Okay, does that make sense? You're going to do it around. That's right. That's right. This is the world premiere of this composition. Oh, 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 1, 2, 3. You're on this side. Oh, there's nobody over there. You guys are on that side. You guys are on that side. Okay, you're the starters. I'll get you started, and then I'm gonna get you start the A. Okay, are you ready? Okay, here we go. 1, 2, ready, play. We should be clapping more than this. Uh, we do it the whole time. We do A, then we do B, then we do A, then we do B. We just keep going. Oh, until you get tired of it. Okay, just keep going. Just keep. Yeah. Well, oh, I'm sorry. I'm so sorry. These little dots mean repeat. Go back to the beginning and repeat. I'm sorry. Oh, okay. Are you now? Are you there now? Yeah, I'm really sorry. Clarity is supposed to be on business, but I've lost it tonight. I'm sorry. Okay, okay. Are we gonna try it again? You're gonna do A, and then you're gonna do B, and then you're gonna do A, and you're just gonna keep doing A and B, right? And we'll have a rhythm going, and so you start at A, and then why don't you guys start right away with B, and then A? Okay, you do that? Are you ready to start with B and then go to A? Okay, and we're all starting at the same time. Does that make more sense? We're gonna try. How am I gonna do that? I know what I'm gonna do. I'm gonna start you guys off, and then when they finish, I'm gonna start you guys off on A, and on A. Okay, come forward. I'm not a conductor. Here we go. Okay, you guys, one, two, ready, go. We're sorry. I got lost. I think now I think that we've we've no yeah, yeah. I think I think I think that at this juncture I'm going to stop with the diversion. I'm losing my concentration, and I just want to thank you all for being such great musicians tonight. Give yourselves a hand. Now, if you have questions of the talk, then I'll be happy to try to answer those. If they don't, if they require knowledge, I'm not sure that I'm going to be able to. Yes, Barbara.
That mathematics and language, you showed a connection. And as someone more schooled in the school of language, I just found that
Oh, cool,
very interesting.
cool. Yeah, yeah. You had not thought about language as mathematics as a language before. Is that right, Rajiv?
I watched that movie called The Man Who Knew Infinity. Have
Yeah,
you had a chance to see that? I was
that was
quite impressed
hilarious.
by the link between intense spirituality and mathematics, where this man says that in the middle of the night, his deity to who he prayed wrote the formulae on the tip of his tongue. That's what he said.
The
He so
deity to whom he prayed knows the formula on the tip of his tongue.
he would write it down.
Knows,
Yes, wrote it down on the tip of his tongue.
it says Ramanujan.
Yes, yes. So so hmm? Yes, he's the one. Yes, yes.
said, I have the proof, but I'm not going to give it to you guys because they're going to publish it.
Oh.
So, and so Hardy invited to Oxford, Union Place, started new mathematics, and there they wrote a number of papers, tried to make me a member of the Academy of Mathematics. He rejected him first time. Next year, when he moved to second article, he accepted it. This was 1915. 1915. So World War started, and he got sick with tuberculosis,
Mm.
and they are hardly tried to send him back home. And then he was only 32. They put him in the ship. He got to Bombay. Bombay made him the professor of mathematics in the college, and he didn't accept him the first time. And then at age 33, while he was working on a problem, one of the blood vessels in one of his cavities in his lung, the fluorescent vessel, ruptured. He bled to death.
Mm.
Bled to death, and he was only married for 1 year. His wife was next to him. So that's the story of Ramanujan, one of the greatest genius of this past century.
Yeah. Ramanujan.
And I want to say something about what makes the mathematics so special. It is the beauty that you said. The beauty is in the symmetry. The symmetry of this equation and shapes. Then also being so concise. So you come and transfer such a great idea in a very concise manner. Einstein's theory of relativity, when he used it, it's tensors, because tensors are much more complex than vectors. But what it's so beautiful and symmetric. And that itself, it just tells you this is the truth. The truth of mathematics is in beauty and in simplicity, yet very profound. Very
As deep as our imagination can carry us. Tom.
Mathematics and astronomy. And listening to you, it struck me that a different way of symbolizing things in a different language was able to go from the abstract but still back into the real world and be predictive.
And did
It's
they?
amazing.
And did they had a completely different system.
Completely.
But that system was also capable of describing this very same world that the Europeans lived in
And
grew
worked,
up in.
yes.
Yeah. That's the amazing thing. These are isomorphic systems, and yeah, nice observation.
Uh, does intuition play a role?
I think it surely does. In fact, that might be the only thing that you have before you have a linguistic formulation of the ideas that you're opening yourself to. The only thing you have is intuition.
Now I understand everything.
Lucky you.
Intuition comes to a prepared mind.
Yeah.
At one moment, suddenly comes out, said, really, uh, speculate, thinking all night about the equation of benzene, stabilize. But we didn't know how the benzene structure formula of benzene. So suddenly in the morning, he dreams, sees this snakes are eating gather, and then he thinks about this not circular, but polygon, which makes benzene, or fixed carbon. Now you can explain this. The whole chemistry, basically, especially the biological system chemistry, Okay, everything else is based on carbon. It was the baby of Cincinnati that just came for intuition, but he had been thinking about it for a long, long time.
That's
He
it.
has exhausted all hazards. Okay, right equation. He, and that's why Louis Pasteur said it only comes in the prepared mind. It's like Fleming discovered penicillin in 1938. Everybody else was looking at this technically bacteria was grown. And you pull away at the end of the week. Therefore, the next step. That day, Fleming looked at one of them and said, oh my God, one of these bacteria has not grown. He said, in a circle around it.
Hmm.
That made him think about why this bacteria, which is supposed to grow, because it has enough nutrients, why didn't it grow? Then he came with the idea of maybe something inhibiting the growth of bacteria, and then he came up with penicillin. Penicillin, you find a fungus. Robert, hey, that is the use of it. And you know what happened after this penicillin? All the infections, almost all of them, responded to penicillin until we became resistant.
Yeah.
1967, not that only probably with streptococcus, certain viruses. I'm just saying that not that you can come up with this thing out of nowhere. I had the pleasure to have such an Everett, Paul Everett, when he was Kalamazoo, University, he would lecture every Tuesday he would come, and every Thursday there was a lecture in mathematics. He would stay in Western Progress. Said, Professor Alan, you know me, said, would you mind asking us? So from that point on, whenever he came to Kalamazoo,
He stayed at her place. Huh?
medical problems, he had some heart problems, he threw a stent and placed it. There. Yeah, and then one night my wife said, you know, this what I know you sound from basement. So I said, well, there is something happening. Although then I see him, it's 3 o'clock in the morning. On the phone with somebody in Calgary, in Canada, talking about an equation which he was working. And he just never slept. I mean, he would be in this table sitting with us. He had this legal pad in front of him, and his eyes were closed. Nose were wide open up. Like, I think he was asleep, but he wasn't.
Mm.
He was just he was thinking. Said, I want to do 1 minute. Want to be a mathematician. And that's why he ended up writing 100 mathematical papers. He didn't do it by himself, but he was with cooperation with other professors. I don't know if you have met Paul Eldridge.
Yeah, 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 yeah. He was at Kate College a couple of times to give talks. Fascinating guy. I just noticed Joe's shirt there in honor of the occasion. That's really very cool. Well, I think that this concludes my report, and thank you so much for giving me your attention and playing along with my little games.